world revolves around the conservation of energy, but sometimes it is difficult to see unless you break down each element. This lab observes and measures the motion of a mass swinging in an arc while oscillating on a spring. From using these observations, a model can be created that shows all the different energy aspects. The results show that tends to be an opposite trend between the kinetic and potential energies, but the total energy always equals zero. One of the fundamental principles that is important in delving into this lab is Newton's second law. Change in momentum equals force times the change in time. This force factor can then be split into total forces. The net force is equal to the spring force and the gravitational force, since the only objects having a direct impact on the mass is the spring and the earth. The magnitude of the net force can be further identified as the spring constant times the distance of the spring plus the mass of the object times the gravitational constant. The next fundamental principle that is important is the concept of the energy principle. This is the idea that energy is conserved. The system is identified as the mass, the spring, and the earth. Since the object and all the interactions are described in the system and no work is being done, there are no other forces interacting, so the total change in energy should be zero. Kinetic energy, which is 1/2 times mass times velocity squared, is important as it describes the object's energy expended during motion. The potential energy of the spring is necessary because it is not constant depending on where the mass is and how far the spring is stretched. This can be calculated by 1/2 times the spring constant times distance of the spring squared. And the last important energy that needs to be considered is gravitational potential energy, to explain how gravity affects the mass, which can be calculated from mass times the gravitational constant times the position of how far it is. From the observations, tracker was used to measure the motion of the mass. Its initial position, velocity, and mass were all either given or determined from the graph. The oscillation time was determined from taking the time for 4 total oscillations to be completed divided by 4, which equaled 1.54 seconds. Going back to the fundamental principles, in order to calculate the net force, the gravitational force needs to be determined. The gravitational force is equal to the mass times the gravitational constant, which in vector form equal to y component of negative 3.94 newtons. The last thing that is needed to determine the net force is the spring force, which is equal to the spring constant times the length of the spring times the direction. First, let's calculate the spring constant. By using the formula, the oscillation time is equal to 2 pi times square root of mass divided by constant. It can be rearranged to solve for the constant, which was calculated to be 6.67 newtons per meter. The relaxed length of the spring then needs to be calculated. At equilibrium, we know that the y forces cancel out, so we can set them equal to each other at this time. By rearranging the equation to solve for the relaxed length, we get 0.109 meters. Now we can take all this information and plug it into our code. The mass, initial position, and initial velocity indicated in the observed data is put in the code, and delta t is set up to be relatively small. Then the gravitational constant, spring constant, and relaxed length of the spring, all calculated earlier, are put into the code as well. Then the updated length of the spring needs to be coded for. The spring position is subtracted from the mass's position to give L, and then to find the direction of L or L hat, it's divided by the magnitude. S can be rewritten for magnitude of L minus the relaxed length. In the next set of lines, the equation for energies described earlier are written into the code, including the total energy, which is just the sum of all the energies. Now the loop can be updated. The total time the observations ran for was 9.212 seconds, so that is the first thing that needs to be updated, followed by the initial energies. Then the forces need to be described. The gravitational force is written how it was calculated in the previous slides, and same for the spring and net forces. Then the new velocity of the mass can be written from Newton's second law, and the new position is given from the updated position formula. The spring is updated using the same steps that were indicated earlier in the code, and next the energy changes needed to be updated by taking the energy formulas and writing delta energy to be the final minus initial respectively. The code is now ready to be run. By selecting the data from the observations, a side-by-side comparison of the predicted and observed data points could be determined. Kinetic energy is represented by the color blue, gravitational potential energy is red, spring potential energy is green, and the total change in energy is orange. The total change in energy stays at 0, so this is the correct depiction of the energies for this system. The second graph shows the comparison of the predicted shown in blue to the observed in red. There is a greater discrepancy as time goes on, which can be due to the fact that drag was not taken into consideration. In the future, by setting up drag component, the predictions versus observations would be closer together. The energy principle states that the energy of the system is equal to the energy of the surroundings. In this case, the surroundings have no interaction with the system, so the total change in energy should be 0, as indicated in the graph by the orange line. In comparing the time periods of the oscillations with the x component, it is 1.66 seconds, and the y component is 1.54 seconds. The difference between the two would create greater discrepancies with the k constant, which would affect the spring force and therefore the net force. The y component needs to be used, though, as it is in the axis as the spring.